Suppose we wanted to find the derivative of a function, but that derivative is difficult to find exactly. There is a way to bypass this difficulty, depending on what we want to do. Here in this lesson I propose finite difference methods, which provide us a numerical approximation to the derivative at discrete points. For the sake of illustration, I have chosen sine x because it is a simple function. Since we know the derivative is exactly cosine x, we have a basis of comparison for the methods I'm about to show. Just keep in mind that these finite difference methods can be applied to any function, not just simple ones. In fact, complicated functions with unwieldy derivatives are perfect candidates for finite difference methods. To start, I have chosen to space the values of x every 0.2 units. This can be called discretization because I proceed to evaluate the function y equals sine x at these discrete points. As mentioned before, we know from calculus that the derivative y prime equals cosine x. This is the exact functional representation, which we also evaluate at discrete values of x. Remember that the derivative represents the slope of a function. Slope is rise over run. For our example here, I have chosen x equals 0.8 to illustrate the concept. Slope is sine 1 minus sine 0.8 divided by 0.2. This quantity equals approximately 0.6205. Compare that to the exact value of 0.6967. This is called the forward difference because we went forward from 0.8 to 1. This is represented visually in the picture shown here. We can compute the backward difference very similarly. Slope is sine 0.8 minus sine 0.6 divided by 0.2. This quantity equals approximately 0.7635. Compare that to the exact value, 0.6967. Whereas the forward difference in this case was a bit low, the backward difference is a bit high. Once again, I've shown this concept visually in the picture here. Now consider a central difference. Slope is sine 1 minus sine 0.6 divided by 0.4. Notice that our delta x is 0.4 instead of 0.2. This slope equals approximately 0.69207. Compare that to the exact value, 0.6967. Thus it is that the central difference is much closer to the true value than either the forward or backward differences. This is related to the h squared in the top of the column. We will explore this connection to the Taylor series in another lesson. What if I chose to space the x values every 0.1 units instead of 0.2? It turns out that our approximations of the derivative become closer to the true value, as we will see shortly. Evaluating the slope at x equals 0.8, the forward difference is 0.6597, and the backward difference is 0.7313. A bit low and a bit high once again, but not as much as before. Similarly, the central difference of 0.6955 is also closer to the exact value of 0.6967. This is similar to the pattern we saw in the lesson on linear interpolation. Basically, the smaller the spacing between x values, the closer our approximation will be to the exact value. A quick note before we conclude this lesson. Notice the gap in the last row of the table for forward difference. Can you think of the reason why we cannot evaluate a forward difference at this endpoint? Let us know your thoughts in the comments section below. Notice, however, that we can evaluate a backward difference here. Of course, the opposite is true in the next column for similar reasons. To truly understand this concept, it is imperative that you practice for yourself. I encourage you to open a spreadsheet like Microsoft Excel and reproduce the example I provided here. See if you can replicate the same results. Let us know in the comments below any insights you gained in the process. As always, thanks for watching.